Greetings. Our paper proposes Sensmart, a sensor data market for the Internet of Things. This work was developed at INESC-ID Institute in Lisbon as a collaboration between the Distributed Parallel and Secure Systems Group and the Communication Networks Group. In this presentation, I will first present the context and motivation for Sensmart. I will then present the objectives and some relevant background and related work. I'll then present the Sensmart solution as well as its experimental evaluation, and I will then conclude the presentation. Context and motivation. The Internet of Things is a conceptual extension of the Internet to encompass the integration of physical or object devices, such that these object devices are then able to communicate their properties, status, or measurements to other machines or human user applications. These entities may in turn issue commands and/or configuration to the object devices. As the object devices may include sensors and actuators, the Internet of Things may be regarded as a global cyber-physical system at the scale of the Internet. The Internet of Things is thus an enabler for innovation and entrepreneurship, allowing companies to create and sell new services based on these object devices, which may be as simple as a temperature sensor or as complex as a drone equipped with a video camera. The enthusiasm brought by the IoT concept led to the development of new service models such as sensing as a service. According to this model, sensor owners may sell sensor data or even rent the control of their devices to interested customers, and all these transactions take place remotely through the Internet. Although sensing as a service exists as a concept, no supporting platform was developed so far. Such a platform could trigger innovative business models for IoT as not only raw sensor data, but also results of analytics processing could be transacted. There are several scenarios envisaged for such a sensor data marketplace, ranging from characterization of air quality in urban environments to optimize directed advertising. Objectives. The main objective of this work was to design, implement, and test a sensor data marketplace where the owners of sensor devices can profit from them by selling the sensing data or renting the sensor devices to interested buyers. The sensor data marketplace should be generic, being oblivious of specific purposes of the buyers. This sensor data marketplace should also be integrated with an existing IoT platform in order to facilitate its dissemination. Two kinds of sensor devices are considered: the simple devices and the rich devices. Simple devices are characterized by higher limitations in terms of energy, processing, and connectivity requirements. A simple device could be a temperature sensor. Rich devices are more complex, but also more powerful in terms of processing capability, presenting more demanding communication requirements. They can be multi-sensor devices or devices capable, for example, of performing audio and/or video streaming. The picture shows simple devices on the left and examples of rich devices on the right. A suitable protocol for simple devices could be MQTT, while for rich devices, their data would in general require a protocol like HTTP. HTTP is one of the most used protocols in the Internet, being the basis of most web services. MQTT was designed for devices with limited communication capability and is based on a publish-subscribe architecture. CoAP is a more efficient alternative to HTTP, but it is not as widely adopted as the other two. The integration with an existing IoT platform aims not only to create the basic infrastructure for the interaction between the marketplace and simple devices, but also to demonstrate that the proposed solution can be integrated with other commercial services and applications, thus facilitating its adoption. After analyzing the available IoT platforms, AWS was chosen due to its architecture, which is very similar to the architecture of MQTT. Each sensor is associated with a virtual device named Thing and a device shadow, through which the state and characteristics of the sensor are registered. All sensors publish their data in topics. External applications or other things may subscribe to those topics and receive the respective published data. The smart city is presented as one of the scenarios with more potential for sensing as a service utilization, since there exists a huge number and diversity of sensors and possible applications demanding sensor sharing. Sensmart, Sensor Data Marketplace. The developed Sensmart architecture has three main components: the device, the broker, and the marketplace. A device module is directly related with the AWS IoT's shadow thing, and the integration of AWS IoT into the device module provides a simpler and wider communication interface for the device module to export. A sensing device publishes its data to its topic via the MQTT protocol, for example. The broker module is the link between the marketplace and every sensor. This module is able to communicate with both device module and marketplace module. The broker defines a set of URLs allowing for the marketplace or device modules to send requests. This is to purchase orders, data, or control comments. The marketplace is the intermediary between the buyer, who wants to gather data from the sensors, and the seller, who has data or sensor control to sell. This module aims to create an environment where, for example, a person can place a temperature sensor on the street where she lives and sell the measurement data to a meteorological service. The marketplace is the core element of Sensmart. Through this platform, consumers and suppliers are able to exchange data and control of sensing devices for currency. The marketplace was implemented in Java 7, and its interaction involved the following 5 elements: customers, persons, or entities that purchase and sell data, and sensing. The devices which collect data to be controlled, and also there are catalogs which store and present sensing devices to the customers. Stock corresponding to the inventory of each sensing device, and broker, which is the bridge between the sensing device and the marketplace. In a typical purchase workflow, the customer initiates the process. The request is then validated by the marketplace regarding the availability of the device. Only then the purchase is processed. Regarding the implementation of simple sensors, there are 3 main constituent elements: the devices in the AWS IoT platform, the data broker, and the data handlers. The data broker is an HTTP server designed to process every data transaction sent from the marketplace model. The data broker isolates the data provider from the data consumer, and this is done to ensure that the consumer cannot bypass the marketplace and later access the device directly outside of the original contract. For this reason, the device is always indirectly contacted. The data handler for simple transactions was designed to send a control message to the device or to request a data measurement and deliver the data to the customer. The sales specification of each purchase request is enforced, and the device is only required to publish data measurements. Thus, The data handler is the intermediary between the sensor and the customer in the data plane. The figure shows the sequence of interactions for a transaction. Above, we can see the customer's request to the marketplace, handling of the request at the data broker, which then delegates the data transactions to the data handler. Below, the data session between the device data handler and the customer through the MQTT is represented. For each sensors, similar concepts apply, though there are some important differences. We are here illustrating the example of a controllable camera. After a successful purchase of a time slot on a reach sensor, the customer will communicate with the sensor via the broker module. With this module, the buyer can control the device or receive any type of data stream, may it be video or sound. In the case of video, the broker module is composed of the video broker, which is the entry point of communication, the handler responsible for managing the customer device connection, the IP-TCP tunnel, which is the communication channel, and the web page responsible for presenting the video stream and control mechanism. It is possible to have more than one customer receiving data from the same sensor at the same time. When there is more than one client consuming the video stream, the handler of it will create a tunnel. For the sensor, the number of customers simultaneously consuming the video stream is not important, since the individual connections are established between the handler and the customers. The figures show the sequence of typical transactions. In the figure below, it shows an example where a camera can be controlled by the customer, there being two data streams, one for control and the other for the video, and both are managed by the handler. Experimental results. Sensmart was tested with both simple and rich device transactions. The first experiment consisted of a scheduled simple data reading task using a simple sensor. The sensor receives the request, takes one measurement, and then publishes it. 3 series of data requests were issued, with each series comprising 100 requests. An overall mean time difference of 1 second.35 was measured between the request and the arrival of the respective data. A long transaction consists of buying all the measurements taken during a given time interval. The sensor performs a series of equally spaced measurements and publishes them during the contracted time interval. Several customers may listen to the data stream at the same time, and in that case, the handler is responsible for data replication on behalf of each customer. 3 series of data requests were performed. In each series, 5 customers require 45 minutes of measurements from one sensor. In this scenario, the mean time difference was 0.5 seconds. Tests were also conducted with a reach sensor, in our case, a controllable video camera. The customer was able to watch the video and to issue pan tilt comments during a contracted time window. Mean to a latency of 200 milliseconds was measured for video control comments, which is quite acceptable. The graphic represents the total HTTP round-trip time of control comments, distinguishing the different contributing causes. Approximately 60% of the total time is due to the communication component. This element is considered to be the time spent outside the handler and customer application. As to the fraction of time spent by the handler, it can be seen that it has mostly to do with TCP message creation and communication. Conclusion. We are proposing Sensmart, a sensor data marketplace for IoT, trying to fill a gap that was still vacant in the IoT architectures. Sensmart supports two classes of devices, simple devices and rich devices, managing their different requirements and characteristics. Sensmart was successfully integrated with the AWS IoT platform, and it was demonstrated and tested in a prototype. There are some clues for future work that we are going to follow. For example, increasing the range of supported devices and services, a design of a web user interface for marketplace interaction so that it could approach other marketplaces, for example, eBay, but now just for sensor and sensor data transactions. The solution also still lacks an improved database support, and it also supports does not still support the transaction of currency, including cryptocurrency. This is something that we are going to integrate in the Sensmart platform. There are also, of course, security and privacy issues that must be addressed. Thank you very much.